So let's get started. Ra- NR. Do you want to sit down? NR. NR. The person would have. It's being recorded and it's going to be published online. So I don't want to name call, you know? All right. So let's continue our journey with the Maclaurin series. I also have loaded some questions that you can try on Google Classroom, so maybe you can try them. Tons of questions to do. So, right. So, what is Maclaurin series? Once again, Maclaurin series is approximating an existing function using polynomial function, and we have already the formal booklet for that, so that's not a problem. We also briefly talked about the Maclaurin series, that it doesn't converge all the time. It doesn't always work. So it only works for certain values of x. So it's not like it doesn't work for certain functions. It doesn't work for certain values of x, where if the x causes the Maclaurin series to be expanding or diverging, then it doesn't work. It only works if the each consecutive term is converging. So how do we know that? We have to check whether if each consecutive term, accounting with the x value and also with the f prime of 0 over 1 or f double prime of 0 over 2 factorial, all together, whether if each term is getting bigger or if each term is getting smaller. There's no need to be like a specific common ratio, but we just have to ensure that each consecutive value is either getting smaller or bigger. We need to solve that inequality. Okay? And then we also talked about this idea of composite function. Composite function looks complicated, but if you try a couple of questions, it's extremely simple, I promise. Basically, what we need to do is we need to find the Maclaurin series of the original function without the compositeness, without the inner part, and then we just replace that x with that inner part, and the question is solved. It looks complicated, but I promise. Like there could be, yeah, this part is kind of getting there, but I'm pretty sure many questions that we do will be pretty straightforward. So why don't we try this question as a quick review? Find by direct calculation the Maclaurin polynomial of degree 2 of sine of each part of negative x. Sine of each part of negative x. It already looks very, very confusing. But I'll start with the innermost part, and then I'll start applying it to a higher degree functions, or the more outer part shells. So, what do I know about each part of x? Well, do I know the Maclaurin series for the each part of x? Well, I for sure do know from the formal booklet that you're not seeing right now, but it's 1 plus x squared over 2 factorial x power 3 over 3 factorial, and so on. The first task is extremely simple, so I'll do it, and then I'll leave the hard one for you. Then, if I know that each part of x is that, how do I find the Maclaurin series of each part of negative x? It's so easy, so I'll do it myself. I'm just going to replace every x with negative x. Which I can then expand it. It becomes 1 minus x plus x squared over 2 factorial minus x cubed also the dot. That's easy, right? I'm pretty sure no one has a problem with this. Hopefully. And also, we know from the formal booklet that sine of x can be represented as x minus x cubed over 3 factorial plus x power 5 over 5 factorial. Then the next question is, what is sine of e power of negative x? This one is slightly more complicated, so I'll let you do it yourself. Yep.
Are you pulling that topping into the bottom?
Basically, yeah. It is disgusting, but we're only looking for the polynomial of degree 2. So hopefully you can disregard many parts of it. So if I plug in each power of negative x into each of appearance of x, it will become 1 minus x plus x squared over 2 factorial plus, not plus, minus x cubed over 3 factorial plus dot. We don't need, but I'm just going to write it down first. 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, the power of 3 divided by 3 factorial, plus 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus dot to the power of 5 divided by 5 factorial. That part is simple. Not the complicated part is after this. Now, the question's only asking for the polynomial of degree 2, or a Maclaurin series of degree 2, which means I'm only looking for just 3 terms. I'm just going to look for that constant term plus coefficient of x plus coefficient of x squared. I just need to fill in the blank, basically. Now, we'll do the constant term in a second. Will you be able to find any x terms anywhere else? I'm specifically looking for, not the first part. How will you find the x terms in the cube of that? If I expand, let's do a side law on the side. 1 minus x. If I do that multiplication, what will happen? What is my first term? I think the first term is just 1, for sure. But then how will I do the second? Mind-boggling. I think we might have something like, well, we got 1 by multiplying each of the first term. But then wouldn't there a term be where we multiply 1 by negative x? Would you say that? Because remember that we're just like foiling or multiplying the same term multiple times. We're just going like, okay, 1, multiply all the terms of the rest. And second term, multiply all the terms of the rest. Vice versa. So I think we will have 1 and 1 and negative x as one of the first one. We'll also have negative x, 1 and 1. Will we have that? Would you agree with that? I think so. And then also, finally, negative x, 1 and 1. Why am I only looking for x? Because I'm looking for the coefficient of x. I think it'll be 1 minus 3x. Minus x minus x minus x. I think this question is kind of getting out of our hands very quickly. Now we need to. Degree 2, is it really? Should we just find it degree 1? I think to find the degree 2, we don't actually have to do it. But one way to do that would be to go with x squared over 2 factorial times 1 times 1. That'll be one of them. And then we just do that 3 times. Then we could also have negative x times negative x times 1. 1 times negative x times negative x. And negative x times 1 times negative x. The other way. That's also 3 of them. I think we could have plus x squared over 2 factorial with 3 times of it minus 3x squared. Plus dot dot dot. But we're not interested. Sorry? Plus 3x squared. It's actually plus 3x squared, yeah. Because it's negative x times negative x times plus. I think there is actually a pattern here then. And do you think we can quickly find this? Wouldn't there be? I think so. This one will be 1 minus 5x plus 5x squared over 2 factorial plus 5x squared. Wouldn't that be? So now I think we can replace it. Which is equal to 1 minus x plus x squared over 2 factorial. I'm just going to stop here because I don't need to find the cubics. Minus 1 minus 3x plus 3x squared over 2 factorial. It's actually computed from here. 3 over 2 factorial is 3 over 2. 3 over 2 plus 3. 6 over 2. 9 over 2. So fix this one. Divided by 6 plus 1 minus 5x. 5 over 2 plus 5. 15 over 2. Divided by 5 factorial. What's 5 factorial? 120. And I think the answer must be, if I did the correct thing. I'm quite dubious about this one. But if I did the correct work, my approximation must be 1. So in the first term, I'm just going to take the ones digits. 1 minus 1 over 6 plus 1 over 120. You see what I'm doing? I'm just taking the ones. That is not a multiple of x. And then the coefficient of x would be -1 minus -3 over 6. So that's positive 1 over 2. And then my next term would be plus -5 over 120. So minus 5 over 120, which is minus 24. 1 over 24. And lastly, it's going to be 1 over 2 minus 9 over 2 divided by 6. 9 over 2 divided by 6 is 9. 3 over 2 divided by 2, 3 over 4. Plus 15 over 2 divided by 120. What is 15? 120 divided by 15? 8. That'll be 1 over 16. Right. We're not going to proceed anywhere from here. This probably sounds like a calculated question. And then maybe I can try to use decimals to see if it's actually true. Should you check it? Sadly, you won't see the screen with the decimals, but let's try to graph sine of e to the power of negative x in a radian mode. And one sine of t, but that's sine of e to the power of negative x. And the blue curve is the approximation. So I guess at least for x equals 0, or close to that, my approximation seems pretty fine. Right. I hope you realize doing the complement itself is fine, but the algebraic within that is kind of complicated. So hopefully you're able to differentiate, hey, this is difficult and that's not difficult. Hopefully. Hopefully. All right. Let's move on. The later sections are pretty similar, but just more applications of it. Part D is section D, 24D, is extremely simple. It's just addition and subtraction. So basically, it's a polynomial. So now we can add and subtract the given things together and represent it as one Maclaurin series, basically. Right. Why don't we look at one of the examples here? Apparently, start the title. Addition and subtraction. This is not exactly in the curriculum, but there is a thing called sine h of x. Have you heard of that? Sine h of x. So, according to the textbook, this is called a hyperbolic sine function. Do you use in your calculator? I don't think so. But I think you can see on the decimals actually, sine h of x. I have no idea where this is used, but probably in like higher level math or higher level physics courses, could be used in hyperbolic sine functions. But what's more important to us is that what is this defined as? According to the textbook, sine h of x is equal to e to the power of x minus e to the power of negative x divided by 2. So then the question is, can I find, let's say 2. Can we find the second degree Maclaurin series for the hyperbolic sine function? It's a lot simpler than you think it is. I'll give you some time, maybe like 2 minutes, 3 minutes to get started, and then I'll chase behind you. If you care to come here during this bit, maybe you should try to learn something. I can't say anything to anyone who didn't come, so I'm going to say stuff to people who did show up. Would you agree with that, Leona? I didn't say your last one, though, so I don't think YouTube will know that. If you forgot what e to the power of x is, e to the power of x is equal to 1 plus x squared over 2 factorial plus double. Right. Seems like a lot of people who are working, seems like they're getting some results. So given the e to the power of x, what is the e to the power of negative x again? We simply just replace every x with negative x, right? So that's going to be plus x squared over 2 factorial, which then I think we can find e to the power of x minus e to the power of negative x divided by 2 quite easily. It'll be 1 plus x squared over 2 factorial minus 1 minus x plus x squared over 2 factorial divided by 2. So that things cancel out quite easily. If they do get cancelled easily. Should you just do one more term, just for fun? We didn't write it here. Plus 2x, and then the next one would be 2x squared over x cubed over 3 factorial, was it? Divided by 2. So it's just x plus x cubed over 3 factorial. Plus, I think we can see the pattern already. What will be the next term? X squared 5 over 5 factorial. Sorry? Only the odd terms, yeah. Interesting. So hopefully this one is very short. On the textbook, it's like 2 pages, and just move on to the next one. By the way, just for fun. So what is this hyperbolic sine function? I think we can do it as sine h of x. Interestingly, I think, unless there's another. apparently on the decimals. I'm pretty sure you can find it on the calculator, on this calculator too. There's a hyperbolic sine function. I don't exactly know if we do have one here, sadly. But yeah, it's there is that. So it's a function that looks like this. It kind of looks like a cubic function. And then let's try the graph what we just had. X plus x cubed over 3 factorial plus x power 5 over 5 factorial. Oh wow, cool. Look at this. This is a purple graph. This is the degree of 5. Almost identical. So accurate. So I would say that this is the level of convergence. Interval of convergence is probably X for all of these numbers. We did extremely well with Maclaurin series. Right. Only for E. Okay. This part is kind of the fun part, where we do the differentiation and integration. Kind of feels weird that we just did addition and subtraction, and now we're doing differentiation and integration. But here we see the usefulness of learning about Maclaurin series. We just learned in the previous section that sine h of x is defined as, not defined as, is approximately, or is defined as e power of x negative minus e power of negative x divided by 2. And then we also found that it's approximately x plus x power 3 over 3 factorial plus x power 5 over 5 factorial, and repeat it. Then, can we find the derivative of sine h of x? Well, we could do the derivative of e to the power of x minus e to the power of negative x divided by 2. But I think we can also do it using the Maclaurin series, which is extremely simple, given the nature of the polynomial function. It becomes 1 plus 3x squared over 3 factorial plus 5x power 4 over 5 factorial. So easy that I did it already without even doing the middle part. Differentiation was pretty easy for the middle part too, but what about integration? Can I find the integral of sine h of x? Do you think I can do that? Also using the integral of the Maclaurin series instead of doing the e to the power of x minus e to the power of negative x divided by 2, which is still pretty simple for now, but still integration is much, much, much easier. We'll have x squared plus 1 over 4 times x power 4 over 3 factorial plus 1 over 6 times x power 6 over 6 factorial, 5 factorial, sorry. So this is the power of using the Maclaurin series. It can be used to find the expression, Maclaurin series of unknown other functions that we don't know yet. Or we can also use it for differentiation and integration. Sometimes you'll be questions that are impossible to find the integration of. Just like some questions that we learn about. I think you probably did see it in like 10 PAP when you first learned how to use calculator to solve equations. Remember learning about how to solve equations that are impossible algebraically? We use graphical method. Right? We just go y equals left hand side, y equals right hand side, and then we find a point of intersection, and then we find the approximate value spread. Same thing. Some integration is impossible to do without without using graphical approach. Well, now here's another method we can do approximately by representing the given function in Maclaurin series instead, and then doing the differentiation or integration. I'll fix it myself. Differentiation is always possible, but integration sometimes is impossible. Why don't we look at that example that indeed that is impossible to do without it. Here. I want you to try this yourself. Part A. Find the Maclaurin series for cosine of x squared. This is a lot simpler than the cosine of each part of x. Promise. Promise. Then find the approximate value for integration of cosine of x squared from 0 to 1. And then we can also check using calculator by actually doing the 0 to 1 cosine of x squared and seeing if it's actually equal to each other. And we're going to start. Maybe I should write down the cosine of x. We don't have to sneak to your formula booklet. Apparently, cosine of x is equal to, according to the formula booklet, 1 minus x squared over 2 factorial plus x power 4 over 4 factorial. Apparently. Is that right? Yeah. Oh. Next time you're looking for is cosine of x squared. So we don't need to put cosine. There's two options. One, take this and have this like instead of this at one. Sometimes when you're trying to catch two words in one cell, you don't get it. Right, MH? Alright, so let's do, what is, if cosine of x is that, what is the value of cosine of x squared? Can I find a Maclaurin series for cosine of x squared? Well, hopefully it's not a rocket science here. We simply put x squared in place of x. It was that easy, yeah. It's not 45. It's 42. Right? From here to here, x changed to x squared, x changed to x squared.
You don't need to find the Maclaurin for x.
No, no need to. Maclaurin's first series for x squared, that's x squared. Strict plane strategy. Well then, let's find the, okay, let's actually go one step further. X power 4 divided by 2 plus x power 8 divided by 4 factorial, 12. Then integration of from 0 to 1 of cosine of x squared of dx would be integral of 1 minus x power 4 over 2 plus x power 8 over 12. Yep. Thank you. Hey, don't blame for the hard work and paying attention. So it'll be x power 5 over 5 times 2, really? Plus x power 9 over 9 times 24 minus dot 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 0 to 1. So obviously 0 is 0, so that's fine. So let's plug in 1. 1 minus 1 over 10 plus 1 over 24 times 9. What's that? 240 minus 24, 216. Is it? I feel so smart whenever I do that. Plus dot 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 will be my final answer. Is that actually true? Well, let's use our calculator. Math function integration. I'm going to use the calculator function today. Went from 0 to 1 of cosine of x squared with respect to x. And I got approximately 0.99999969538. And then let's compare that to 1 minus 1 divided by 10 plus 1 divided by 216. Probably got a similar result, hopefully.
What's the answer?
According to my work, 0.904905.
If it was anything but a polynomial, we'd have to get the Maclaurin series again. Like the x to power 2, we only put it in raw because it's a polynomial already, right? Like if it was
Yeah, good question. So by the way, if I found the exact value in the calculator, it was 0.9045, and this value was 0.9046. So we're pretty accurate with that. Now, good question. From before, in the previous question, we tried to do the sine of e power negative x. Well, e power negative x is not a polynomial. So we need to find the Maclaurin series of that, and then do the final Maclaurin series of sine of that. In the last question, it was cosine of x and then cosine of x squared. X squared is a polynomial. So we don't do that. If it were, let's say cosine of sine of x, for example, then we'll do a Maclaurin series of the Maclaurin series.
So it's already
No. Because the whole purpose of the Maclaurin series is approximate using a polynomial.
I'm picking up what you're putting down.
just wait until it's like cosine of sine of e to the power negative.
Because this was like the most like because this was like the most like
Yeah, true. But yeah, you see that both side of x squared is definitely possible to experience, at least using our current knowledge.